Good afternoon, guys. Today we're covering lesson 89, which is the average value of a function and the mean value theorem for integrals. There's a really good example on page 456 if you'll read through that. There are two tanks shown at the top of the page filled with water. One of them, the water is just stagnant. It's not moving. So we can clearly see that the area of that would be the length, which would be b minus a, times the height, which is h average. Then if you look on the other side, the one on the right, somebody touched the tank. But the water level the water itself didn't change, it's just moving around a little bit in there. So we have that curve up at the top to find the area of that tank. Remember, that's just the integral. The definition of integral is it's the area bounded by a curve in the x-axis. So the integral there of that tank would be the definite integral from a to b of f of x dx. Alright, well, we know that the amount of water in there is the same. They're the same tank, no water left, no water was added. So we can set those equations equal to each other. So we have b minus a times h average is equal to the integral from a to b of f of x dx. And if you solve that for h average, you get 1 over b minus a times the integral from a to b of f of x dx. So if you look at the bottom of the page, it says the definition of the average value of a function is if f is a continuous function on the closed interval I from a to b, where b is greater than a, in other words, b is on the right-hand side of a, then the average value of f is given by the average value equals 1 over b minus a times the integral from a to b of f of x dx. Okay, so look over on page 457. First example. Find the average value of the function f of x equals x squared minus 10 on the closed interval from -1 to 2. Okay, so x squared minus 10, that's a parabola, so it's continuous everywhere. So we can use this. So the average value will be 1 over b is 2 minus a is -1 times the integral from -1 to 2 of x squared minus 10 dx. You guys don't forget to put that dx in your integrals. It's impossible to integrate without that differential in there. Some of you gotten pretty sloppy about that. Okay, so now 1 over 2 minus a minus 1 is 1/3. And now we'll integrate this. So that will be x cubed over 3 minus 10x, and we evaluate that from -1 to 2. So that will be 1/3 times, plug in 2, that would be 8/3 minus 20, and then plug in -1, so that'll be minus 1/3 plus 10. So the average value is going to be 1/3 times, that'd be 8/3 plus 1/3 would be 9/3 or 3 minus 20, and this minus times 10 would be minus 10. So that's minus 30 plus 7. So 1/3 times -27 is equal to -9. Now, what does that mean? If the average value is negative, it means that most of the area of this curve lies under the x-axis instead of on the top. And if you look on page 457, it shows you that parabola, the vertex is at -10. So yes, on this interval, most of the area is below the x-axis. Okay, so moving on page 457. 89.2 says approximate the average value of the function f of x equals 4e to the 2x on the closed interval from 0 to 3. Okay, well, e to the 2x times 4, that's a continuous function. It's that exponential curve. So we're okay to use the formula. So the average value will be 1 over b minus a, so 1 over 3 minus 0, times the integral from 0 to 3 of 4e to the 2x dx. Well, that 4 is a constant, and this becomes 1/3, so you can pull the 4 out here and put it over 3, and then we're going to integrate e to the 2x dx. And remember, our formula is for e to the x, not e to the 2x, so you can either mentally or you can write it down. U is 2x, so du is 2 dx, and there's a 2 that's not here, so we have to take 4/3, multiply it times a half, and then we can integrate e to the u, du. And the integral of e to the u is e to the u. So this will be, let's see, 2/3 e to the u, but e was 2x. Oh, and I somehow forgot the u. 0 to 3, and I'm going to put x equals 0 and x equals 3 because it's pretty simple just to plug that back in. And that's from 0 to 3. So that will be equal to 2/3 times e to the 3 times 2, so that would be e to the 6 minus e to the 0. And if you get a decimal approximation for that, or you can just leave it like that, is fine, or e to the 6 minus 1. The decimal approximation is 268 I don't even know what just happened. Let's go to the next page. 268.29. I don't know what just happened, guys. I don't understand all I know about this thing. Here we go. 0.29. There we go. All right, so that's the average value of that function. Now, over on page 458. It talks about the mean value theorem for integrals. So remember the problem about the speeding ticket one? It just tells us that somewhere in that interval, the average value had to be equal to that number in order for that to have happened. Well, this is the mean value theorem for integrals. And it says that if f is a continuous function on the closed interval from a to b, same thing as what we were dealing with average value, there exists at least one number c between a and b such that f of c, which is the y value, is equal to 1 over b minus a times the integral of f of x dx. The pictures at the top of page 458 are wonderful for demonstrating this, so I want you to really look at those. So the last example says, given that the average value of f of x equals 2x cubed on the interval from 0 to 3 is 27/2. Use the mean value theorem for integrals to find some number c such that f of c is equal to 27/2. Well, we can't use the mean value theorem to find c. We just use the mean value theorem to know that, yes, that is a continuous function on that closed interval. So we know that what the mean value theorem says is true, which means that f of some constant that we're going to find has to be equal to 2c cubed. And they tell us that that average function is 27 halves. So we put 27 halves for the y value, and we solve it for c. So if we multiply by 1/2 on both sides, we get 27 over 4 is equal to c cubed. So c will be equal to the cube root of 27 over 4, which would be 3 over the cube root of 2. And if you get a decimal value for that, it comes out to be 1.8899.